Hello, everyone, and welcome to The Biggest Ideas in the Universe. I'm your host, Sean Carroll, and this is the Q&A video associated with idea number 5, I believe it is, called Time. Somehow, I managed to go through the entire actual video on time without mentioning the most important fact about time, which is that I wrote a book about it. This is very important for authors to mention. My publisher would be very mad at me if I didn't let you know that From Eternity to Here, The Quest for the Ultimate Theory of Time, it's the first trade book I ever wrote. It discusses much of the things we've already talked about in the last video, the eternalism versus presentism stuff, a little bit about relativity and time travel, and is mostly about entropy and the arrow of time and some of the cosmological scenarios that could lead to that, as well as some of the implications. We're going to mostly get to relativity and entropy later in the series. So I know there's a lot of Q&A questions about relativity, general relativity, special relativity, entropy, one way or the other. Not that I'm ignoring those questions, but they will be addressed later on, and the book addresses them in great detail, so you might want to check that out, available wherever books are available. I mean, what else are you doing? You're reading, you're learning new things. So if you've discovered my videos or my books more recently, this was a 2010 book that I'm still quite proud of, and it's all about time. So moving into the questions, again, I'm going to be more inspired by the questions and go through a little literal order of them. There was one sort of set of questions about whether time is real and what that really means. And I think that I just didn't do a very good job of explaining what I was trying to do in the first video when I talked about whether time is real or not. So maybe just putting it in slightly different words will help the basic ideas come through. So, is time real? Time real? The answer is yes. But different people might claim that the answer is no, not because they have a different notion of time, but because they have a different notion of what the word real means. Again, as I said in the first video, everyone knows what it means when you say be at a certain place at 8 p.m. That's a completely useful, in fact, necessary concept for getting through the day. So time is absolutely real in that operational, pragmatic sense. But there's two other kind of distinctions that you might want to draw. One is fundamental versus emergent. And I think this is what a lot of people have in mind when they say that time is not real. What they really mean is that it's not fundamental. So the analogy I always use here is, it's not an exact analogy for this case, but it gets the general idea across. If you think about a box of gas, okay? This is the kind of thing that physicists will often do. I don't know why my pen is skipping. So we know that a box of gas is made of atoms, molecules, little particles of gas rolling around inside the box, bumping into each other. So there's a way of talking about the box of gas that says it's made of particles. Depending on what the gas is, there might be atoms or molecules or whatever. But there's another way of talking about the gas that says it's a fluid. Gases count as fluids, so this means it has, a temperature, a pressure, density, and it's a smooth, continuous thing. Now, we thought back in the day, before we knew about atoms, that gases just were fluids, and this is the most fundamental description you could make of them. We realized in the 19th century, that in fact the air around us is made of atoms and molecules. Other gases are also made out of atoms and molecules, so that the gas is not really smooth and continuous like a fluid would be if you get down to the microscopic level. So we know now that a more fundamental description of the gas is in terms of the particles. As far as we know, you can completely describe the gas in terms of the particles, whereas you cannot completely describe it as a fluid. There's certain questions you might want to ask about the gas that can be answered using the particle description, cannot be answered using the fluid description. Nevertheless, it would be silly to say that it was an illusion that the gas is a fluid. In fact, we use the idea of the gas being a fluid all the time. We talk about its temperature. We talk about the temperature of the air outside, the atmospheric pressure, the velocity of the air, all of these things that make perfect sense in the fluid description, but not in the gas description. That's okay. This is the more fundamental description in terms of particles. This is the more emergent description because it comes out only at this higher level of abstraction. It's It's both that you look at it sort of from above, you sort of squint and you fuzz over all the individual microscopic idiosyncrasies of the particles, or you can say that in terms of the domain of validity of this description, the particle description is valid in more situations. Like if there's only one particle in the box, the particle description is still perfectly good, but the gas description is not. The emergent description is generally true as an approximation in some particular domain of validity or domain of applicability. But that doesn't make it any less real. It's perfectly okay to talk about the reality of the fluid. And I think that time is exactly like that. There's a lot of people who will say, well, time is a way of talking about the relations between different parts of the universe in some more fundamental, timeless description. But that doesn't mean that time is somehow an illusion. It's just emergent, but it's still just as real as if it were fundamental. If you believe that tables and chairs, people and planets are real, then you should believe that time is real. But there's another notion, another sort of way of slicing this problem that is a little bit different. And rather than saying fundamental versus emergent, we can talk about passive versus active. And this is a sort of slightly different distinction that some people have in mind when they say that time is real or is not real. What I mean by that is, in the block universe perspective that we talked about in the last video, I'll draw the universe literally as a block, okay? So this is space, these two dimensions. This is time going up this way. So one moment, like the present, might be a little slice of the universe, like this. So this is now. To somebody, of course, to people in the past or the future, they will call their moments now, but this is part of the nomenclatural difficulty of dealing with the block universe. And in this picture, in this block universe picture, time is just a coordinate. Time doesn't make anything happen any more than space makes things happen. Time is just a way of locating events in the universe. That event is in the future of what we have labeled now in this particular picture. Whereas there's a picture of time that does not really fit well with the block universe picture, but one in which time is either is, or at least is associated with, bringing the universe into existence. So somehow time is the thing that takes you now and moves you into the future. I'm not sure exactly if anyone would talk in exactly those terms, but this is the basic spirit behind what they're saying. And this is a distinction that goes along with a different point of view on the nature of the laws of physics themselves. It's not exactly a one-to-one. For any of the professional philosophers in the audience, I apologize for glossing over a lot of important details here, but in spirit, this picture of the block universe goes along with something called a Humean perspective, not human, Humean, as in David Hume, view of the laws of physics. And this other view doesn't have a person really associated with them, so it is called anti-Humean. And the difference is that the Humean view simply says the laws of physics are an encapsulation of all the stuff that happens in the universe. So what is real in the Humean view, what is important, what defines the nature of reality, is everything that happens, all the stuff that there is, and the configuration of that stuff at every moment in time, at every location in space. Or if someday we replace space-time with some more fundamental structure, then whatever the collection of stuff is, the collection of physical happenings, that is the universe. And a Humean would say the laws of physics are just patterns obeyed by the actual stuff. It's the stuff that matters. The laws are just a convenient description of the stuff. Whereas an anti-Humean really thinks of the laws of physics as creating the universe. The laws of physics have some extra oomph to them over and above just being a description. And again, since I'm more of a Humean mostly myself, so I'm not exactly sure the most convenient and effective way to put this into words, but they really think that there is some reality to the becoming. Very roughly in sort of Heideggerian terms, this is being and this is becoming, okay? Again, very innocent looking words with many, many thousands of words of philosophy underlying them if you want to talk about them in different ways. I'm not going to talk about this difference in great detail right here. If you're interested in the distinction, you can look at the podcast I did with Ned Hall, who is a chair of the philosophy department at Harvard, and we talked about this Humean versus anti-Humean view of the laws of physics. But you can see how it relates to time. If you're Humean, if you just think the laws of physics are a description that is convenient for us, then time is just a label, right? It's just where are you? Which event are we talking about right now? Whereas if you're anti-Humean, time really has a much more active role. It's bringing the universe into existence. So there are those who, when they say the phrase, time is real, I consider time to be real, what they mean is that time is not just a coordinate. Time has a more active role. I think that people like Lee Smolin fall into this camp, although he should speak for himself. That's my understanding of what he's trying to say. So when they say time is real, they don't just mean time is either fundamental or emergent, but time is a useful description. They mean time is doing something active, playing an important role in bringing the universe about. I think that time is real, but I also think that it's passive. I think that time is just a coordinate, just a label. It's not bringing anything into existence. There's no oomphiness to time. It's just a convenient way of talking. But it's still real, just like I think space is real in exactly the same way. So that's just some nomenclatural clarification. If you hear people saying, oh, unlike others, I think time is real, maybe what they mean is they think that time has an active role to play. Okay. There's two more little nomenclatural cleaning up jobs we have to do. One is the block universe, if you're an eternalist and you believe in the block universe. Some people say, well, if you live in the block universe, then, if you believe in the block universe, then you think that the universe is static or it is unchanging. So how can, sometimes they say these final words out loud also, how can change ever happen? Isn't this in conflict with our experience of the world, since we seem to be thinking about the world as changing all the time? And this is, I tried to explain this, so I'll try to explain it again. I think maybe I'm just getting something unclear myself here. It's my fault. But the point is, to a block universe person, here's the universe. The point of the block universe is that all moments of time are equally real, okay? It's not that reality is the three dimensions of space at one moment of time, and reality used to be something different and will be something different in the future. Reality is the whole four-dimensional shebang. That's what the block universe person believes. So it's easy to look at this picture and say, look, there's nothing changing, right? If I just erased this label there, then it just looks like a block. So nothing can possibly be changing. But the point is, if you believe this, you just have to be careful about what you mean by the word change and static. In the block universe, what you mean by change is that what is happening here is different than what's happening here in the block universe, okay? At some different moment of time. That's what change means. It means that not all these slices are the same. Change is the difference between one slice and another. It's not something that happens to the four-dimensional universe as a whole. So, again, I think this is, in some sense, down to our linguistic inadequacies, because the language was invented long before these concepts were invented. We think, and when you use words like static or unchanging, you're assuming a certain notion of time that is not quite appropriate to this four-dimensional block universe. In the four-dimensional block universe, the differences that we're talking about between one time and another are relational. Compared to one earlier time, there's a difference at some later time, okay? Between those two times, things changed. The universe, the state of reality at any one of those moments is not the same as the state of reality at a different moment. That's what it means to be not static. That's what it means to be changing. The whole thing isn't changing. The whole thing encompasses change. The four-dimensional world describes change, but it is not itself changing. I hope that made some sense. That's the point. So you don't need to say, if you're a block universe person, that there's no such thing as change, the universe is static, or anything like that. Finally, there's the question, along a related vein, don't we observe the past? So this is an argument the other way around. This is an argument, isn't the block universe obviously right? Because I can look out into the sky at stars and galaxies, and relativity teaches me that the light from those stars and galaxies travels at 1 light year per year. It took a long time for it to get to us. So what we see when we look outside is the state of the universe, of these stars and galaxies, in the past. So a pro-block universe person might say, isn't it obvious that the past is just as real as the present because I am observing it when I go outside, okay? Sadly, no. Even though I believe in the block universe, this argument doesn't quite convince me of anything. And the reason is, if you're really strictly 100% careful, when you go outside and you look at the sky and you see stars, etc., you're not looking at the past. What you're seeing is not the past. What you're seeing is light hitting your eye right now, at that moment. But there's an additional step where you say, well, because the light hit my eye at this moment, I infer a certain thing about the past. Namely, there was a star or galaxy shining in a particular way that created that light that got to me. But that's in your mind, right? You are creating a connection between the thing you see right now and the conditions of the universe in the past. It's not quite right to say that you're actually observing the past. You're inferring something about the past from your present observations. Okay, now let me get to a couple of more substantive questions, less about language and nomenclature and so forth. Basically, one question that sort of gets asked in different ways about the reversibility of the universe, or in similar words, the time symmetry. So I made a big point in the first video of saying that if you reversed everything in the universe, so if you were at the microscopic level, looking at something that was not big and had entropy and dissipation and everything, but just had a small number of moving parts, you could make a movie of it, you could play it backwards, it would look the same. This is a feature of the fundamental laws of physics as we understand them, that they can go either way in time. You can take the universe right now, if you're Laplace's demon, you can predict both the future but also the past because of this reversibility feature. So people try to come up with a couple of examples where they say, well, this doesn't look reversible to me, and let me sort of explain what's going on. So one is gravity. The idea here is that gravity only goes one way, right? Gravity only pulls us together. That's what gravity does. Isn't this, someone might say, an example of irreversibility? Things only fall down. Apples fall from trees. Apples do not spontaneously leap up into trees because gravity is always pulling them down. So this is a little bit of a mix-up between the fundamental laws of physics and the macroscopic ones in the case of the apple, but there's also something even at the fundamental level going on. You have to really understand what is meant by reversibility. So let's say that here's the ground and here's a person, and this person throws a ball up in the air, okay? So the ball goes up in the air and it will fly in a certain trajectory. It goes up and it comes down. The point of the reversibility of gravity is that if you took the ball right here, which now has a velocity pointing toward the ground, if you ran time backward and reversed that velocity, it would go exactly backward. Let's see if I can do this. It would go exactly backward on exactly this same trajectory and get to exactly the same point. So anything that is a solution to Newton's equations for gravity and for motion forward in time is also a solution backward in time. So the fact that gravity pulls things together, that's true. But when you reverse not only the fact that the ball is over here and going down, but you reverse its velocity also. You say you move it in the other direction. And there's different ways of thinking about this. One way, the simplest, most naive way, is just to say, look, the velocity is the derivative, the rate of change of the position with respect to time. So if you reverse time, you reverse the velocity, right? Velocity equals dx dt. So when t goes to minus t, that implies that the velocity goes to minus the velocity. There you go, okay? So that's the aspect of reversibility we have. So general relativity, Newtonian gravity, Newtonian mechanics, all of these things are 100% reversible in that sense. What we really mean by reversibility is you can start with the situation at one moment in time and go either forward or backward without losing information. So there's another example people asked about, which is what about radioactive decay? This is maybe looking forward a little bit, but that's okay. We can talk about it. So there's a rule that if you have a nucleus with a lot of particles in it, more particles than I'm going to draw here, but you have some nucleus, and over time, the nucleus can decay. And let's see if I can redraw this. Looks more like a bunch of grapes, doesn't it? So get rid of that, and let's say that one of these particles spits out, an electron or a photon or something like that. Or there's more dramatic ways it can decay. It can split in two. But the point is, in the rules that we are taught, you cannot predict exactly when the nucleus is going to decay. You are given a probability per unit time that the nucleus is going to decay. So in some sense, it cannot be run backwards, right? Like if you have a nucleus, if you have the nucleus that is already decayed and you look at that, you don't know when it decayed in the past. You can't sort of run the movie backwards. So I'm going to kind of punt this example a little bit because, of course, this involves quantum mechanics. And quantum mechanics is not classical mechanics. And quantum mechanics is a much subtler story to be told about reversibility. I mean, the reason why I'm saying that is because we don't know whether quantum mechanics is reversible or not at the fundamental level. You may have heard that there are controversies about what quantum mechanics actually is, what the real formulation of it is, what the fundamental ontology of it is. And different versions of quantum mechanics have different perspectives on reversibility. Some of them are reversible, some of them are not. The many worlds interpretation has this in-between stance where the wave function of the universe as a whole evolves in a completely reversible way, but any one branch does not look reversible because we see less and less of the wave function of the universe as time goes on. So that's how you finesse that in many worlds. But all I'm going to say right now is radioactive decay doesn't count for any of the talking I was doing about reversibility because it's not part of classical mechanics. Oh, and the final one, very similar here. What about violation of T symmetry in particle physics? You may have heard of this. So in particle physics, field theory, really, quantum field theory, which again we'll talk more about later on, but there's three discrete symmetries that play a crucially important role in particle physics. There is C, which is charge conjugation, which is basically the word came about, the label charge conjugation came about because you reverse the sign of the charges of elementary particles. Like an electron with a negative charge under the C transformation becomes a positron with a positive charge. But really what it means, the electric charge just goes along for the ride. Really it's a matter-antimatter asymmetry. You swap particles for antiparticles. It's a discrete symmetry because you're not smoothly rotating between an electron and a positron. You're discretely just switching. Electron goes to positron. And it has this property that if you do it twice, you come back to where you started. Electron under charge conjugation goes to positron. Positron under charge conjugation goes to electron. Likewise, there is a symmetry called P for parity, which is basically mirror reversal, right? You know that when you look at something in the mirror, it looks like left to right has been switched. So roughly speaking, if you have axes, X, Y, Z, these are axes in space, parity takes these and flips their orientation. So one way to draw it would be X, Y, Z. So you go from what's called a right-handed coordinate system to a left-handed coordinate system. It's mirror symmetry in that sense. Be careful, because in string theory, there's an entirely different symmetry called mirror symmetry that has nothing to do with parity. Sorry about that. And finally, there's T, which is time reversal. And that literally just reverses the direction of time, as you know. So it turns out that you might think that these are all very good symmetries in nature. If you changed all the matter in the universe for antimatter and vice versa, you might think it's completely the same universe that you're in. Turns out not to be true. Every single one of these three symmetries, charge, parity, and time reversal invariance, are not completely satisfied by the real world. In actual particle physics experiments, there are things you can do, like the decay of a neutron, where if you held them up to a mirror, okay, the rate at which that situation would happen is different than the rate at which the situation originally happens. So there's a violation of parity symmetry. Likewise, time reversal and charge conjugation are both individually violated. So you might worry, you might say, well, wait a minute. You've been saying that the universe is time reversal invariant, and now you're telling me it's not. Now, of course, what I've really been saying is that classical mechanics is time reversal invariant, and this is modern quantum particle physics, but that's not the little loophole I'm going to use in this particular example. The loophole I'm going to use here is that you need to be careful about what you mean by time reversal, okay? So let's think about what is actually meant by time reversal. Remember when we did the example, I just did the example of the ball. I'm going to ignore the person here, but a ball that's thrown up in some trajectory, goes in a parabola, falls down here, and has a momentum or a velocity, let's call it momentum, when it first leaves. And then down here, its momentum is more or less in the opposite direction. I can probably do a better job of drawing it like that, okay. So this is at time t2, this is at time t1, okay. Let me do a little bit better there too. This is for posterity. You should do a good job. So when you do the time reversal, if you start with x at time t1, the position, and p at time t1, the momentum, you don't just flip it. I shouldn't say t1. I should have said t0, t2 there. So what I mean is the time that at the end, it doesn't matter. I can do time reversal invariance whenever I want, but I'm examining the situation when the ball is just about to hit. I want to rewind the clock, right? So I'm doing my time reversal reflection, as it were, my time reversal transformation at the moment just before the ball hits the floor, which I've called T2, okay? So to do the time reversal, to ask the question, what does it mean to run the clock backwards? What do I do to x and p, to the position and the momentum? Well, x stays the same. X goes to x, so this is time reversal invariance, so it goes to exactly what it was, x at time t2, but I reverse the momentum. It becomes minus p at t2. And you say, well, that makes sense because back up here, I said time goes to minus t, therefore velocity goes to minus velocity, and momentum is just mass times velocity. That's the Newtonian way of thinking. In the Hamiltonian way of thinking, remember we talked about the idea that position and momentum are fundamental, right? That you don't think about momentum as being defined as mass times velocity. It works out to be that, but that's not the definition. Momentum is a fundamental thing all by itself. And that's the point. In order to make the statement the laws of physics are invariant under time reversal, you need to be very, very specific about what it means to reverse the direction of time. You don't just run the clock backwards. You change the fundamental variables that you're evolving at the same time. When you go to electricity and magnetism, for example, the magnetic field reverses its direction when you do a time reversal invariance. So the answer to the time reversibility of fundamental physics, given that T is violated, is that think about real time reversal as a combination of C, P, and T. That is to say, you take the system you have, you hold it up in a mirror, you reverse the direction of time, and you change particles with antiparticles, okay? This symmetry, which I can invent, which involves reversing the direction of time, is, as far as we know, a perfectly obeyed symmetry of nature. There's no violation of it. So the violations that we observe of t and p and c individually cancel out when you do all of them at once. In fact, this is a theorem under certain reasonable assumptions, quantum field theory with the symmetries of special relativity, etc. CPT is always going to be true. You can violate it by violating those assumptions, but experimentally, as far as nature is concerned, CPT seems to be a perfectly good symmetry. And that's all we need to say the laws of physics, as far as we know, seem to be reversible at the fundamental level. Just don't use t naively as your time reversal operation, use CPT, and that makes perfect sense to us. Okay, now having said all that, that was all the actual questions, but I want to talk a little bit about there's a set of issues here that get mixed together that all relate to each other concerning time travel. Ooh, that was a bad job of writing there. Travel. Determinism. And free will. I'm not going to give the once and for all correct story of free will here in this video, but we can talk about it a little bit because it's relevant to the question of time and time travel. So by time travel, I mean in particular travel into the past, right? And let me just say this in words because it goes by very quickly. Of course you can travel in time to the future, right? I did that yesterday and I traveled 24 hours into the future and here I am now. That's sort of a trivial old joke that people use. I've used it myself many times. What you mean by time travel is generally travel into the past. So is time travel into the past possible? If Isaac Newton had been correct, right, if space and time were absolute, which is what we've been talking about so far, you have time here, space here, then no, travel into the past is just not possible. You just get older. The rule is you can only age into the future. The same thing is true in special relativity, Einstein's 1905 theory of speed of light being the maximum and things like that. But in general relativity, GR, we're going to get the GR later, but in general relativity, space-time is curved, okay? Which means that you can curve so much that you can actually imagine going back to the past. And the simplest way to do this is through a wormhole, okay? So I'm not going to draw a space-time diagram. This is just a space-space diagram here, but here's a wormhole. You've heard about these things in science fiction movies, etc. A wormhole is a situation where you can hop in one side, go through it, and come out the other side. So it is in principle a shortcut through space, because even though I drew it this way, so it looks like it takes longer through the wormhole, the distance from one end of the wormhole to the other might be very, very short. So I can't draw it that way on this particular piece of paper. Sometimes you see it drawn like this. So imagine that you fold over your two-dimensional illustration of space to look like this, and then the wormhole is just sort of connecting one side of this to the other, like that. So then it really does look like a shortcut. Well, the thing is, if you can travel faster than the speed of light, you can go backward in time. This is something we'll talk about soon in a different video. And so that's what a wormhole lets you do. It lets you travel apparently faster than the speed of light by taking a shortcut. So what Kip Thorne and others realized is that if you have a wormhole and you can take a shortcut through space, you can also take a shortcut through time. In fact, you can synchronize one end of the wormhole and the other at different moments of time. So you, as far as the universe is concerned, hop in the wormhole at one moment of time and you can get spit out in the far future or the far past. So in principle, this is a space-time diagram in principle. I don't think this can actually happen in the real world, but here is a general relativity space-time diagram. Time, space. But now there's a wormhole. And this, remember this, oops. That was not very good. This is a space-time diagram. So the wormhole is going to look like two little circles at any one moment in time, two little spheres, one in which you go in and one in which you go out. And the rule is, if you hop in the wormhole at this moment, I just made up this rule, but it's okay. The idea is I'm allowed to make it up. I pop out over here at a much earlier time. And then I could imagine traveling backward, or traveling to the left, and visiting myself before I hopped in. So that's a real time machine. That's really going backward in time. Clearly I'm skipping steps and leaving out some niceties, but this is the basic general idea. So in general relativity, where you can curve space-time, it is at least possible to imagine traveling backward in time, visiting yourself in the past. This brings up logical paradoxes, right? The grandfather paradox. What if you went and killed your grandparents before they met and gave birth to your parents, or your father or your mother, and then where would you come from? Or what if you just changed history, right? What if you traveled back and killed baby Hitler? Baby Hitler is usually the person that gets chosen for being killed. Wouldn't that leave you in a completely different universe? And this gives rise to paradoxes and some weird movies and stuff like this. So I'm going to give you the two simplest ways out of these paradoxes. The first simple way out is time travel is not possible. So we don't actually know whether or not in general relativity situations like this with the wormhole sending you backward in time are actually feasible, are actually possible to imagine doing. We can imagine them. What we can't prove one way or the other is whether they are doable in the real world. It seems from a bunch of different investigations that if you tried to make a time machine this way, what you would actually end up making is a big black hole that would just suck you in and never let you leave. We don't know of any robust, provable way to send yourself backward in time. So that's the cheap way out. The next best way out is whatever happened, happened. This might be familiar to those of you who are fans of Lost, of the TV show. They went the time travel route in later seasons, as many TV shows do. But they actually did a pretty good job of it. You could travel backward in time in the world of Lost, the TV show, but the point is that when you go into the past, from the point of view of your present self, that past already happened. So the rule was you could go into the past, but not change the past in any way, because it already happened. Whatever happened, happened. If you go into the past and do something, that thing you did was always true in your personal past, okay? Lost is not the first TV show or movie or story to have this rule in it, but they have this fun motto, whatever happened, happened. You can buy t-shirts with this motto on it, okay? And what that means is, like, let's say you go back in time and you somehow find a time machine, a wormhole or something like that, and you try to kill baby Hitler. Well, under this theory of time travel, you will fail. I can't tell you why you will fail, right? I can't tell you what stops you, but I know you will fail because Hitler did not die when he was a baby. Hitler really existed. This is a way to get out of the apparent paradoxes of time travel in classical physics. Now, parenthetically, there's also the possibility of quantum mechanics, right? And if you believe in many worlds, you might think I could go to a different branch of the wave function. David Deutsch and others have talked about this possibility, but to be honest, I do not think that it is really understood how that would work. But certainly you can hand wave your way into saying, well, you're in a different parallel reality, so the rules are different. Not talking about that right now. What we're doing is imagining the rules under which time travel could be valid in a classical universe. And the answer is if and only if whatever happened, happened. We know that Hitler wasn't killed as a baby, so if you can go back into the past, whatever happens to you does not include you killing baby Hitler, okay? Now this bugs us. This is why it's a paradox. I mean, you say, well, but I have my time machine. I go back there. There's baby Hitler, you know, no one's guarding him. No one knows he deserves to be guarded. I have a gun. What's to stop me from doing my job and killing baby Hitler? And the answer is we don't know, but you will be stopped. So this bugs us because it seems to be a conflict between the past versus our free will, right? We think we have the ability to go and choose to kill baby Hitler, but we also know the past is fixed. The past already happened and baby Hitler did not die. So this seems to be a conflict. Whereas when you imagine going into the future, seems to be less of a conflict because we don't know what happened in the future. Okay, so this is where the determinism parts of this. Oops, what do I do here? Yeah, this is where the determinism parts of this story come into play. If you believe in Laplace's demon, the past and future are equally fixed. Okay, so time travel, because it mixes up your personal future once you hop into the time machine with the past of the universe, because it's already in the past, that gives us a sort of a bad feeling about our free will, because our ability to make choices seems to conflict with the fact that the past is fixed. But really, if you're more careful about it, the same thing is true about the future. Everything is deterministic if you believe in Laplace's demon. Again, if classical physics were true, which it's not, etc. So you didn't have any free will in that sense either. The difference is only that you don't know what the future will actually bring, and therefore you feel like you have free will toward the future. Now, I'm not going to give the whole free will speech here, as promised, but there are those of us, called compatibilists, who think this fact that we don't know what's going to happen in the future, and we never will know, right? It's not like, well, we don't know yet, but we'll find out. We'll never have the ability to predict the future with perfect accuracy, or even anything close to perfect accuracy. That means it is perfectly sensible to talk about making choices and having the ability to do one thing versus another, because we just don't know. It might be baked into the laws of physics and the state of the universe today, but if you don't know it, that has absolutely zero impact on how you get through the day. Nobody literally goes around going, well, I'm not going to choose what to do today. I'm just going to let the laws of physics work their magic, okay? When you walk into a restaurant, the old joke goes, and the wait staff comes up and says, what would you like for dinner? You don't say, just give me what the universe has determined I'm going to have, okay? You make a choice, and it's that effective making of a choice. It's back to the emergent versus fundamental. Free will is not fundamental. It's not built into the laws of physics at the microscopic level, but at the macroscopic level, when we describe human beings, it's absolutely crucial to talk about human beings as making choices. So again, I'm not going to give the full defense of that compatibilist point of view, but I want to let you know that it's there if you're wondering how we can possibly reconcile our ability to make choices with a deterministic Laplacian universe. And let me give you one final fun example about this exact puzzle. This is an example called Newcomb's paradox. Some of you will be very familiar with this. Some of you are in for a treat if you're not already familiar with this. So Newcomb's paradox, William Newcomb suggested the following idea. You are shown two boxes, okay? Box 1, box 2 are put on a table in front of you. And this box is transparent, and this box is opaque. This is one of those philosophy thought experiments where you're offered a choice and you're asked what you want to do. So in the transparent box, you see there's $1,000. There it is. It's right there, yours for the taking. In the opaque box, you are told that there's either $1 million or $0. You're not told which one, okay? And you're sort of at this point, if you're not familiar with the puzzle, you're guessing what's going to happen. You're asked, do you want the $1,000 box or do you want the opaque box with either 0 or $1 million? No, that is not what you're asked. What you're given the choice is, you can choose. Call this box A, box B. So your choice is, you can choose to take either only box A, get the $1,000. You can choose either box B, if you want that, you want to take the risk, right? Or you can choose both. I bet you weren't anticipating that, were you? You could just take both boxes, right? At this point, you're saying, well, wait a minute. I will choose to take both boxes because I know there's $1,000 in box A. Whatever's in box B, I don't know. but if I choose to take it, I'll get it. If it's zero, it's zero. If it's a million, it's a million. I might as well choose, right? The boxes are already there. It's not that anyone's going to fiddle with the boxes after you make your choices, okay? The boxes are there. They're sitting in front of you. So there's clearly one perspective which says, no matter what, I should just take 2 boxes. The decision theory argument is there's an expected value of taking 1 box, $1,000. There's expected value of taking both boxes, $1,000 plus some fraction times $1 million, okay? The fraction of likelihood that the $1 million is actually there. Here's the complication. You knew there was a complication coming, right? The complication is there is an oracle. I'm going to draw the oracle as a looming red blob. Okay? There you go. That's the oracle. Well, actually, the oracle is called the predictor, I think, in the... So the predictor is some being that has access to what is going to happen in the future, okay? Or at least knowledge. You can think of the predictor as maybe Laplace's demon, if you want to be mechanistic about it, or you can think of the predictor as something that has precognition, something that has the ability to actually look at the future and see what will happen. And the predictor says the following. So let me write this in red. I'll make it a little smaller here. The predictor tells you something before you make your choice. The predictor says, if you choose just to take box B, to leave A there, okay, then box B will have $1 million in it. Whereas, if you choose both, B is empty. This is Newcomb's paradox, okay? So the predictor is the spanner in the works. The predictor is the thing that makes it a non-trivial problem. The predictor, which we believe, or have good reason to believe, super duper really good reason to believe, is 100% accurate. The predictor is predicting the future, and the predictor says, if you choose both boxes, you're going to get $1,000. If you choose only box B, you will get $1 million. So this is a paradox. This is the tension. On the one hand, the money's already there. Okay, there's either $1 million in box B or there's not. There's a very sensible, logical set of statements that says I can only make more money by taking both boxes than by only taking one. The other argument says there's a predictor who's always right about the future, who says that there's a future in which I get $1 million by taking only box B, and a future in which I get only $1,000 by taking both boxes. Okay, so this becomes a raging debate in philosophy circles. You can actually, if you go up to a professional philosopher and say, are you a 1-boxer or a 2-boxer? They will know what you mean. You're referring to Newcomb's paradox here. Should you take the 1 box or should you take both? And I am a 1-boxer. I think that you should just take box B and get the $1 million. If you really, 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 really believe that the predictor is always accurate. And the reason why is because I believe in the block universe. I believe that basically the way you should think about it is this. There is something that happens in the universe. And we're ignoring, again, classical versus quantum mechanics, multiple realities, anything like that. Okay? Let's imagine we also somehow knew that the universe was deterministic. Basically, in my view, what is going on here is there's 2 possible histories of the universe, one in which you take both boxes and box B is empty, the other one of which you take only 1 box and box B is full of $1 million, okay? And what the predictor is doing is telling you that the real world, which is unique and determined, is one of those 2 futures. You can imagine a different future in which you took both boxes and box B had $1 million in it, but the predictor is telling you that the real world is not that. That's the information that the predictor has given to you. So if that's what's going on, and you're choosing between 2 possible futures, you don't know which one you're in, but you're given the ability to choose, make one actually come true. Now you can believe, the reason why I think this is an interesting way to think about free will is, You can say to yourself, well, I'm made of atoms. My atoms obey the laws of physics. They're going to choose one thing or another. Okay, so which universe I'm in is actually secretly already determined, even though I don't know it. Fine. But that is completely irrelevant to the fact that you need to make a choice right now. You need to choose one box or both, okay? You can sit there and say, well, it's determined which one I will choose. Fine, but choose, okay? You don't know which one you are in. For all intents and purposes, in the real world, you are faced with not exactly this kind of problem, but you are faced with choices to make based on the fact that you don't know what the determined block future of the universe actually is. And the way to think about that is, I'm ignorant about the future, but I can make certain choices that make certain futures come true rather than others. In my view, in Newcomb's paradox, you can make the universe come true. You can locate yourself in the universe where you make $1 million by choosing to pick box B rather than both boxes. There are people who disagree. Okay, so there are people who don't quite believe me about this. So be it. That's why philosophy is an interesting thing. Usually, I think that these puzzles typically are paradoxical because they're slightly ill-posed. Like in this case, it's not ever completely filled in how the predictor gets their information about the future. Like, are they really Laplace's demon, or do they just have precognition, or whatever it is? Are they creating the future somehow? But given the setup of the problem, I think taking one box is clearly the right thing to do. It's a nice way to reconcile. If it already fits in, I personally came upon Newcomb's paradox long after my views on the block universe and compatibilist free will had already developed. But anyway, it's sort of the future version of the time travel paradox, right? The time travel paradox is I go to the past and I am seemingly limited in what can possibly happen. Newcomb's paradox is sort of taking a piece of information from the future and bringing it into you right now. It gives you an equally paradoxical situation. That's why thinking about time is a lot of fun.